Good afternoon, folks. It's 4 o'clock. I'd like to get started. I wrote myself some notes, and there's a lot. It's my pleasure to introduce today's Colloquium speaker, is our own Margaret Murnane. Margaret got her bachelor's and master's from University College in Cork, Ireland. If you listen carefully during the talk, you still might be able to pick up a little bit of Irish accent. She then came to the United States and got her PhD at Berkeley in 1989. She took academic positions at Washington State and the University of Michigan before coming to CU Physics and, of course, JILA in 1999. Since joining CU, she's been a pioneer in the areas of ultrafast X-ray science and the use of femtosecond scale lasers for X-ray generation. X-ray generation, and she's the director of the Strobe NSF Center since its inception. She has authored or co-authored over 500 papers, and she has also co-founded the laser company KM Labs. Her list of awards and accolades would take us all day to cover fully, but let me just list a few highlights. She started early, winning the Rosenbluth Outstanding Doctoral Thesis Award from the APS. She won a Sloan Foundation Fellowship in 1992. In 2000, she won a MacArthur Fellowship, also known as the Genius Grant. In 2012, she won the Willis Lamb Award for Laser Science and Quantum Optics. In 2017, she won the Frederick Ives Medal and Quinn Prize from the Optical Society. In 2021, she won the Benjamin Franklin Medal in Physics. And in 2022, she won the Isaac Newton Medal from the Institute of Physics in the UK. She's a fellow of the Optical Society, the American Physical Society, and the AAAS, and she's a member of the National Academy of Sciences since 2004. So today she'll be speaking on the topic of tabletop X-ray lasers, so we're very honored to have her here. Please welcome Margaret Murnane.
Thanks so much, Tobin, for that kind introduction. And today I'd like to tell you about the connection between tabletop X-ray lasers and tell you some stories about the connection between Star Wars and the quantum sculpting that turned out to be key to being able to make a tabletop scale X-ray laser. Tobin, thank you very much for the introduction, but I have to point out, of course, all the work was done in collaboration with our group and Henry Captain. We were graduate students in physics in the same group, and we solved the two-body problem by starting a joint group. So everything is in collaboration with Henry. And so I'll spend the first half of my talk telling you some relatively ancient history that for many of you happened before you were born, but for those of us with who remember the Reagan times have some interesting memories that we're being reminded of now. And then I'll spend the second half of my talk talking about, what do we need to do to make these quantum technologies useful. And in our group, we love lasers, we love laser science, we love technology of all kinds, but of course, nothing works without people. So in particular, I need to thank the early group members who figured out the physics, and current group members, many of whom are in the audience and are pictured here, who are really the people working with collaborators to figure out, well, what can we use these quantum technologies for? And so one of the motivations is, we know that as our devices get smaller, more three-dimensional and more complex in their structure, if we want to design efficient devices, we need to be able to measure their thermal, mechanical, structural, interfacial, electronic, and magnetic properties, and do that in a functional way. See if we made the device right. Does it work efficiently? And there's a critical need for better functional metrologies. We have fabulous microscopes that can take a static image of things, but we have very few microscopes where we can see function at the nanoscale. So that's one of the big motivations, and of course, this is why the US and many countries around the world build synchrotrons and free electron lasers, because X-rays are very good at penetrating samples that are opaque to visible light. They also can tell you what the chemical, elemental, and magnetic state are. Compared to electron imaging, you don't have to cut the sample as small, and they can image with lower dose. And if you have coherence, then you can image at the wavelength limit and capture dynamics, look at a functional property. And of course, coherence means that all the waves are aligned in both space and time. That has been a 50-year or more challenge. And the reason is that if you want to build an X-ray laser based on population inversion, which is what most of our lasers are based on, you would need an enormous amount of power to make an X-ray laser. An X-ray transition means the energy is very high and the lifetime is very short. And so we can make a quick back-of-the-envelope calculation based on the ratio between the spontaneous and stimulated emission coefficients. And if you do that, you can show a rough power scaling that goes as the wavelength to the inverse fifth power. And what that means is that I can hold a laser pointer in my hand, and it's powered off a rechargeable battery, because you only need a milliwatt or less power to actually make the population inversion. But if you want to make a laser at a wavelength of 1 nanometer, you would need a terawatt of power. And a terawatt of power is about equivalent to the electrical generating capacity of the United States. And if you want to make a 1 angstrom X-ray laser, then you're going to need a petawatt of power. And so we're never going to have a continuous wave X-ray laser based on population inversion. And that's why back in the 1980s, which is just about when I arrived in the US, there was a proposal during the Strategic Defense Initiative to use an X-ray laser to shoot down missiles by detonating a nuclear weapon in space. Now, fortunately, that was not actually implemented yet. But as luck would have it, today we got this from the American Institute of Physics that said, you would put satellites in space that then could have a booster that could then shoot down the incoming missile, and as well as the projectile, they also were instructed to look at non-projectile possibilities. So we might just need to, but this will not be, I point out, this will not be a tabletop scale apparatus. Now back on Earth, so of course, we have a beautiful X-ray laser that was not based on population inversion. It is the Lina coherent light source that was demonstrated in 2009 at SLAC at Stanford. It's based on electron acceleration, a completely different technology. It's really wonderful, but it has two issues that means that it is still very worthwhile pursuing a tabletop version. The first you can see, because this is the length of the electron accelerator near the freeway interchange here at near SLAC. So it is a 2-kilometer long electron accelerator. The second issue was, I thought, best highlighted by Steve Chu. Steve was Secretary of Energy when this the LCLS came online. And so he said, it's a marvelous device. It's an X-ray free electron laser, but it's certainly not free. And I should know. And it cost about $2 billion with the upgrades and such. And that's just construction costs. So it will be very hard to scale this to actually, really impact materials development or materials R&D. And so that's why it's also very good to see what can we do on a tabletop. And this is also the reason, this is just sort of interesting if you're not in laser science, that we've had the laser for over 60 years. And it turns out that the shortest wavelength laser that's in widespread use is the excimer laser at 193 nanometers, and that's used to print many of our nanoelectronics. And what's shocking is that this is less than a factor of 4 shorter in wavelength than the first laser that Maiman demonstrated way back in 1960. And in almost every other area of technology, whether it's computing, data storage, everything has progressed by many, many orders of magnitude. But this making tabletop scale X-ray lasers has been just prohibitive in energy. And that's why these high harmonic sources are very interesting, because they are the only current solution for a tabletop X-ray laser source that span from the ultraviolet now into the soft X-ray region. So they are based on scientific discovery. Charlie Rose and his group were trying to understand how atoms ionize in strong laser fields. When they noticed that coming out of their interaction region were harmonics, but not a few low-order harmonics, which is what they expected, but rather harmonics up to the 17th harmonic. And this would be like plucking a guitar string and hearing 17 overtones. You just don't expect it. All the previous experience with harmonics would be that the power drops off very precipitously as you go from one harmonic order to the other. So it clearly was a very interesting observation. People did not understand what was happening at the time. Charlie and his group asked how they are emitted, but the funding agencies told him, just drop it, it can't be very important, move on and do other things. So that was in 1987 at the University of Illinois at Chicago. Very shortly afterwards, or shortly 6 years later, there was some very nice work done at Stanford University and Steve Harris' group, where they saw this spectra. And this immediately told people, so now you have harmonics going from order 21 to over 100. This immediately told you this was not what anybody expected. All the harmonics were the same magnitude, and so people immediately realized they were dealing with a new physical phenomena. And sure enough, that was worked out actually relatively quickly. By 1992, people had full time-dependent Schrodinger equations that explained what was happening. And I'll mention those in a moment, but let me just go over the concept of what's happening. It's Henry likes to say it's a universal behavior of all atoms, molecules, and ions in strong laser fields. The laser field, it's easy with a very modest energy. If you have a 10 femtosecond pulse, it's very easy for the laser field to suppress the Coulomb field binding an electron to an atom. And if you do that, then part of the electron wave function will quantum tunnel. Then it will appear in a strong laser field and then get catapulted on a boomerang-like trajectory, can re-encounter the ion, recombine with the part of the wave function that didn't ionize, and liberate its wriggle energy as an X-ray. And this is happening on every half cycle of the laser. So you get this boomerang-like trajectory, this burst of X-rays, and of course, I know everybody here can do a Fourier transform in their head, and so a periodic emission in time will give a periodic emission in frequency. And so that's the origin of the higher order harmonics. The wonderful thing is the scaling. So the maximum energy one can generate in the harmonic scales as the wavelength squared, as opposed to the scaling for a population inversion, which scales as the wavelength to the inverse fifth power. So it's very easy to make a high energy harmonic. You can sort of think about it also in terms of nonlinear optics, that you're adding up an odd number of laser photons to make these high harmonics. But that doesn't quite show the sort of the beautiful quantum nature. And so to show that, I have a nice movie here from our collaborators, Andreas Becker and Carlos Hernandez Garcia, where what's shown here is an electron, a 2D representation of an electron in the ground state, for example, of hydrogen, and what happens that poor electron when it gets whacked by this very intense laser field. So what you can see from the movie that you, okay, let me wait a little bit until it cycles again. So now you can see that the atom is undergoing tunnel ionization, and this slow sloshing back and forth, those are the half cycles of the drive laser. But because when the electron is in the continuum, it acquires a different quantum phase than the part that's not ionized, you get a beautifully spatially modulated radiating electron wave function. And those spatial modulations give rise to a very rapidly changing dipole moment. So instead of just re-radiating the fundamental frequency, it looks as if you're creating a nanoscale dipole antenna that's radiating at much higher frequencies than the laser that you're using. Leo?
What controls
the sloshing back and forth?
no,
The extent?
the final result? How many?
Yes, yes, yes.
Go by the width of the ball.
Actually, you can just keep on turning up the laser intensity. They're not very bright, but you can keep cranking up, and it really is just at the detection limit. From the point of view of using them, I think the highest harmonics that have been used, even in like toy experiments, is the 5,000 order.
How does it depend?
Okay.
How does it depend on the width of the ball?
So I will get to that, and I'll ask you to make sure, because each atom, it's a dipole transition into the continuum and from the continuum back down. And you know a dipole is not a very directed beam. So the trick is that you need to make the harmonics, and then you need to make the harmonics from many atoms add coherently, and then you get a beam, and then it's useful. Does that make sense? And I'll try and get to that. So that's the answer to that is about 5,000. Yeah. But nobody knows the answer, because to really calculate the answer, you would have to couple the time-dependent Schrodinger equation with the Maxwell propagator, and do that for wavelengths that are like 3 or 4 orders of magnitude apart. And the problem is the time step. If you have a 1 angstrom X-ray, that's a very high frequency. So the time steps you have to propagate, they're just calculationally not possible to calculate those now. But nobody thinks we're at the limit right now, that there's lots more room to improve this light source. And this is a very simple quantum sculpting. We're just hitting the atom with linearly polarized light. We can also hit it with a circularly polarized light. That's shown here in this middle movie. What you'll notice is the atom ionizes, so you're getting the electron moving away from the ion. But the problem is, with circularly polarized light, the field just encircles the atom, so it never returns, so you don't get any emission. But fortunately, there is a scheme where you can get emission if you use 2 colors and have opposite circular polarization. And now we can ionize the atom, but the electron returns, and that's a way to make circularly polarized harmonics. If you prefer a photon picture, the idea here is that you have to conserve photon spin angular momentum and energy. And the only way you can do that is to grab 1 photon more than the other in the counter-propagating light. This is just an example of the power we have to actually control the X-ray emission. And those of you who work with X-rays know that we have very poor selection of X-ray optics. So being able to control the X-ray emission with light is actually quite important for these applications. And there's a nice analogy that of high harmonic generation with the Röntgen X-ray tube, that in fact you can think about it as a quantum coherent version of the Röntgen X-ray tube. So think about it in an X-ray tube. You boil electrons off a filament, you accelerate them in an electric field, and then they hit a target and generate X-rays. So in high harmonic generation, we start with the atom in a coherent state. It undergoes tunnel ionization and then is accelerated in a coherent laser field. And then the part in the continuum recombines with its coherent counterpart, admittedly phase shifted, in the ground state. And so you get every step is quantum coherence. So these are an extremely strong coherence. But back to Leo's question, so Leo wants to know, so how far can you push this? Well, to make a beam, it's non-trivial. If we think about the laser, and this is a viewgraph from Carlos Hernandez Garcia, as a quantum conductor directing 1 trillion atomic musicians, you need to add the field in phase from all those musicians to get a bright beam. And related to what I talked about, that the driving laser field might be 4 micron in wavelength, and this is not to scale. If the generator harmonics are 1 nanometer or 10 angstroms, then for all these trillions of atoms, you have to add the light to within a fraction of a wavelength and a fraction of a cycle. So that means you're trying to add the emission to sub-angstrom. The fields are adding to sub-angstrom spatial resolution and sub-attosecond temporal resolution. And we don't have modulators that can let us do this. So the only way to do it is to try to understand the physics and get the physics to help you. And in fact, that's essentially what happens. So if I make an analogy with frequency doubling, many of you use lasers and then frequency double the light, for example, to change red light to blue. What you do there to build up a strong emission is you want the fundamental and second harmonic to travel with the same phase velocity in a material. Now, we know from the rainbow or from prisms that doesn't normally happen, but if you use a birefringent material, you can propagate one field along one axis, the other field along a different crystal axis, and pick the magic angles so that they add coherently. For high harmonic generation, this was very hard for people to figure out, and what I mean by people, it's the whole community. It took us a long time, and the reason it took a long time is that it was conceptually different from what you do in visible nonlinear optics. It turns out in high harmonic generation, instead of phase matching in the spatial domain, you have to phase match in the time domain, because the laser starts out moving in a neutral gas, so that's like glass, so that slows down the laser light compared with the X-rays. But then as you ionize the medium, you make a plasma, the phase velocity is greater than the speed of light in vacuum, so the laser light moves too fast. So there's only a finite time window when the X-rays and laser will travel at the same speed. And so, of course, like when we discover these new phenomena, they're always useful as a means for control. And what they let us do is a very simple way to make these ridiculously short pulses. For example, if we use the widely used Ti-sapphire near-infrared lasers, we phase match over many half cycles, and that emission in time gives us harmonics in frequency. But if we go to, 1 or 2 micron, 2 or 3 micron lasers, we phase match only a single recollision. And so that's a coherent Bremsstrahlung. So instead of making harmonics, you just make a coherent, a supercontinuum that that spans 12 octaves, so the broadest supercontinuum to date. So I hope I've given you a sort of some ideas as to why this process is very interesting and is just a beautiful process to control with laser light. We need that control. As I said before, it's hard to get good optics in the X-ray region. And from the point of view of applications, almost all applications of laser light really demands very precise control. And now we have that control at short wavelengths. Okay, so let me first talk about applications that might use time resolution, and then I'll talk about applications that use the temporal coherence first, and then the spatial coherence. Now, as we learned how to make faster and faster snapshots of the real world and then the nano world, we could see different processes and understand them better, because if you can actually see what's happening, you can check if your theory is right and such. And so as we moved from camera flashes to strobe lights to ultrafast lasers, we were able to look at rotations, vibrations, and then almost the only things that are happening on sub-femtosecond timescales are spin and charge dynamics. The electrons are very light, they move very quick, they can scatter off each other. But one thing that many people didn't understand is that there was a fundamental sort of transition in how to do ultrafast science as you went from femtosecond lasers to these attosecond harmonics. And the reason is the uncertainty principle. That if you look at a 10 femtosecond laser and then ask, well, what bandwidth do you need to support that light? So we can write the uncertainty principle in an energy time formulation. So if your time is 10 femtoseconds, that's a bandwidth of 1/10 of an EV. That precision lets you probe different orbitals or different bands in a material. And since a lot of the things you would like to learn about, you know, spin excitation, charge scattering, all of those will be different for different electronic bands. So if you try and measure those with an attosecond pulse, you're not going to get very far, because your attosecond pulse will be 10 to the minus 3 here. That means you need a keV bandwidth, and it's very hard to you have to be very careful about how you make those measurements, and you have to be very careful about how you interpret them. And the community is still grappling with this on how to do this well. You can make good measurements, you just have to be very careful about how you design them and interpret them. And what's sort of interesting is that, you know, if you ask, you know, so what are the big applications of ultrafast lasers? It turns out that the big applications are in multiphoton microscopy and in laser micromachining. So they are enabled by the ultrafast laser, but they're not ultrafast measurements. And this is a very beautiful image from Chris Zhu's lab in Cornell. It's a 3-photon microscopy of deep into a mouse brain. And, you know, this is just my personal bias. I think harmonic sources are heading in the same direction. And it's really driven by sort of materials needs. If we try to characterize functional nanoscale properties at dimensions below 100 nanometers, that's below the wavelength of visible light. So if you shine visible light on a nanostructure and try to interpret the scatter pattern, you have to have a model to help you interpret it. But if you don't know the physics, then you can't make the model. So there's a big need for smaller rulers so we can actually characterize functional properties. And the challenge is only getting harder as we try to make more energy efficient devices with better interfaces, more controlled transport. It's getting harder and harder. And although we have amazing electron microscopes, we've got a gorgeous new facility here at CU Boulder, to make a high resolution electron image, you either have to kill the biomaterial and then cut it, or cut the nanomaterial and you can only image a very tiny sliver of it. So what would we really like to do? We'd like to be able to take a functional device and look at a movie of heat, charge, and spin inside one of these devices to see if we made them right. Instead of throwing engineers at the issue and making 100 or 1,000 versions and testing them all and trying to do just the trial and error approach. I like to do that a little bit more smartly, and then also image living biological processes without killing the sample. And there is a chance that this will happen, and maybe one of you will end up actually making this possible. Okay, so in my area of science, we believe that high harmonic sources can see better and see things as they happen, but you have to also pay a lot of attention to engineering, because if your source is not stable, you cannot do a hard experiment. The other thing, as we try to figure out, so where can high harmonics, contribute to science and technology, is we can't do that alone. We don't have the materials expertise. So we're very excited and grateful to a whole bunch of collaborators from national labs and industry who really work, side beside our students, bringing us samples, and really coming to us with challenges where they don't have a current commercial solution. And so this is exactly the sort of thing we should be doing in the Science and Technology Center. And in every one of these applications, we can measure something that you can't measure other ways. So, for example, Anya and the magnetics team, they can look at a magnetic alloy and see the magnetic state on each element in the alloy. Or Iona and Eric are looking at the spin texture in a magnetic material. Also looking at buried interfaces, understanding the fields at a buried interface is very important for many devices. And today I'd like to talk about building better microscopes. And I think Marcus is here. Is that right? Thank you, Marcus. So Marcus, Henry, myself, Gordana, lots of other people here at Boulder and UCLA and Berkeley worked very hard to try to get a science and technology center that started in 2016. And the pitch we made was that if you look at the most advanced microscopes, whether they're electron microscopes or light-based microscopes, that you don't get a direct image. So it's not like the microscope that we use in high school. And so you have to use an algorithm to reconstruct the image. So we have to combine better hardware toolboxes and better computational toolboxes to actually push the imaging to the quantum noise limits. And just to give a few examples of the types of things we've been able to do, one of our strobe collaborators at UCLA, Hong Zhao, a former student of his was the CTO of Moderna, and Hong had the ability to gather enormous amounts of data to make high-resolution images of the Moderna vaccine. So Hong and his students worked all through the COVID pandemic in helping Moderna to see if the changes they made to the outside of their vaccine were what they expected, so that the vaccine could be stored at regular freezer temperatures and not at the much lower temperatures that needed a med school facility. Also, predictive heat transport. I mentioned before 3D spin textures, and beautiful results from Marcus's lab on new low-dose methods to image delicate materials. So what I'd like to tell you about next is how this ability to make laser-like beams at short wavelengths is really revolutionizing X-ray imaging. And the reason is we do not have the ability to make a perfect X-ray lens. no material will refract X-ray light, and so people use diffractive optics called zone plates. But the precision at which you need to make them is so high that the best X-ray microscope that has been made is at best 10 times diffraction limited, or 10 times worse than the wavelength of the light. And all this changed with the advent of these coherent harmonic sources, synchrotron sources, and X-ray free electron sources. Because if you have this laser-like beam, you can shine it on a sample and collect the scattered light. Normally, in a microscope, you would use a lens to reconstruct the image, but we don't have a decent X-ray lens. So instead, we use what's called a phase retrieval algorithm, a computer algorithm, to retrieve the phase, and then of course we can make Fourier transform and retrieve the image. And this has totally revolutionized synchrotron, XFEL, and harmonic-based microscopes to really be able to measure things that people would have thought impossible 10 years ago. It has a nice, this technique has a very nice history. It was first proposed by David Sayre way back in 1952, and in a paper titled Some Implications of a Theorem Due to Shannon. The two interesting things about this paper is it's sad to see this is the whole paper. And would you look at the last line, and can anybody ever imagine getting this by a reviewer these days? The extension to 3 dimensions is obvious, which is, of course, but the other very interesting thing about this paper and David Sayre is he's also a co-author with John Miao on the first paper to experimentally demonstrate coherent diffraction imaging. John fought with the guys at Brookhaven to do the experiment. It was a very, as you could imagine, the first experiment in any field is very crude, so the images weren't very interesting, not as good as you could do with a traditional X-ray microscope at the time. But of course, as we know, algorithms are, getting more and more powerful, and so this technique actually is now working very beautifully. But it took a while because the first algorithms are very crude. This was work that Richard Sandberg did back in 2007 using very simple algorithms where we milled a little J for JILA in a piece of metal, stuck it in the beam, and got a scatter pattern. We didn't know the phase, so we assigned a random guess to the phase and took a Fourier transform. You could see a little bit of, could recognize the J here, but there was also a lot of things that we knew were not part of the image because the piece of metal blocked all the visible light, so it must be a wrong guess. So in these old algorithms, what people used to do is, well, they would say, they call this shrink wrap, so we know that that is wrong, so let's take the part of the image that was required to be isolated, and now Fourier transform, then replace the intensity of the scatter pattern with the experimental values, which we know are completely correct, but now we had a better guess of the phase. And then you could run this for a long time, and then it would converge, and then if you ran 200 different convergences, and then average them all together, you would present that to your material scientists and said, oh, this is your material. But of course, the material scientists didn't want an average image of their sample. They wanted the actual image of the sample. So what made that possible, in many years since, is just better data collection. For example, if you scan the beam over the sample, but have a lot of overlap between adjacent scan spots, that's a lot of redundant data that forces the algorithms to converge. And so this technique of coherent imaging has gone from where the industry folks would look at you and say, that's far out, we cannot believe this, to where, many companies, semiconductor companies now have programs in this area because it lets you see more information. And one nice thing that in the extreme UV region of the spectrum, photon energy is around, let's say, from 30 to 100 eV. The very nice thing about that photon energy range is that material still reflects in this region. So this is the reflectivity of different materials as a function of incident angle from grazing. So that's the intensity difference. And then there's also a phase shift, because in coherent diffraction imaging, you get the amplitude and phase of your sample and illumination beam. So you get contrast from both the phase and reflectivity. And this is, and you can clip a piece of material, load it up into a microscope, and you don't have to cut it, because in the soft X-ray region, materials don't reflect, so you have to build a transmission microscope. In the EUV, we can build a reflection microscope. The Royal We, this was Michael, Chrissy, Yuka, Nick, and many more people who contributed to this. This was one of the harder experiments we've ever done, because what they had to build was a microscope where the CCD camera can scan, and then the little sample holder can do this tachographic scanning with overlapping regions. And then we were fortunate to have some good collaborators who gave us some challenging samples so we could show that the microscope actually works. You can make a spatial image of a nanostructure, and then at any position you can actually look underneath. This is model-based, and tell what the composition is as a function of depth, what the interfaces look like, what the interfacial roughnesses are, what the dopant profiles are. So this is very interesting for many devices. And then some of our collaborators pushed us further. So 3M came to us and said, so can you tell us what our metamaterials look like? So the metamaterials, they are materials, for example, that might be used to put an anti-reflection coating on a solar panel. But to engineer their optical properties, the little structures here are sub-visible wavelength, so you can't look at them with visible light. The holes are too deep for AFM, and if you put them in an electron microscope, you can melt the structures. And you also have to cut them to put them in an electron microscope, and so polymers squish, and so things you're trying to see, you destroy by trying to do the sample preparation. But Nick and Clay and Oliver very bravely stuck a polymer in our reflectometer. We didn't know if we were going to make, organic mush, but it turns out we didn't. They mounted the different structures, looked at this was a very simple experiment. They just looked at the scattered diffraction pattern from the 2D structure. They didn't even need to do this fancy tachographic imaging. And they were able to show, yes, indeed, they could figure out the shapes and the structures and extract the layered thicknesses and densities and such. And the only other way to make a good an image was a very special type of transmission electron microscopy that we worked with Steve George and Sadeh Yazdi on, that you had to do an atomic layer deposition to protect the polymer structure, and do that in a very deep nanostructured material, and then coat the sample for the electron imaging. So it would be prohibitive to actually use that as a general metrology method. Then this coherent diffraction imaging and tychography, it's not magic. It works great if you have a complex sample. But some of the samples people would really like to use it for are periodic samples. This is a gate-all-around transistor or some other nanostructure that you care about being able to measure. But from the case of highly periodic samples, you get all kinds of artifacts. Essentially, the diffraction patterns don't change, so your algorithms have very little information to work with. Fortunately, structured light comes to the rescue. I told you how we make circularly polarized harmonics. It turns out we can also make vortex or orbital angular momentum high harmonics This is used very powerfully in super resolution imaging. It's used, for example, in STED microscopy to deplete the emission from a very small region of the sample so that you can enhance the resolution of visible imaging. So we can use this trick, but in a different way for imaging periodic samples. So what Bin and Nathan did was show that if they used a Gaussian, just a normally shaped harmonic beam to image a periodic sample, they would get diffraction patterns, but the algorithm totally told us the incorrect answer, that it was a tartan pattern and not a periodic structure. And the reason why is shown in this movie that Nathan made, which is scanning a Gaussian beam on this periodic object, and then as you scan the beam, the diffraction pattern doesn't change. So your algorithm really has no way to get a good image reconstruction. But if instead you use one of these complex vortex-shaped beams that are very highly diverging, then if you scan that over the sample, you can see that you get a lot of diversity in the scatter patterns, and this helps the algorithm correctly reconstruct the object. And the other thing they were able to show was that in the case of a very delicate object, like a 20 nanometer carbon grid, that when they imaged it with SEM, the electron beam milled away the sample, whereas we could image multiple times using the EUV beam. These EUV photon energies are only around 40 eV, so much, much lower than the electron beams in an SEM, for example. And this is Bin and Nathan and Juan and Peter graduated in fall 2023, and this is them the next day after they graduated in the December 2023 graduation ceremony, and they were skiing in their graduation regalia, so they got a lot of they got a lot of high fives as they were going down. Okay, so let me then end in the next few minutes by just looking at, you know, what are we excited about, and it is really, now that we sort of understand how to make good stable beams in the extreme UV region of the spectrum and work with others to show that we can measure things you can't measure otherwise. Some of the things we're very excited about is expanding into the vacuum UV and soft X-ray region of the spectrum. And this is being enabled by high-frequency trading gift to science. So this is called an anti-resonant hollow core fiber, and the light is guided by these tiny little structures, and normally for high-frequency trading they're used because if you compare them to a regular optical fiber, the light will travel slower in the optical fiber than in air, and so they can do their trading faster. Now for us, this was we don't do high-frequency trading, so but they also guide the light really efficiently, and we can stuff these fibers with a lot of atoms, which we need because the individual atomic nonlinearity is very weak, so we need a whole bunch of atoms. So suddenly we have a way of near as close to lossless for us as, and we can make the royal we means that Will and Clay and Jeremy and Drew and others are just got very good at mounting these fibers and then showing that we can actually make very stable VUV beams. And just today, I don't have it in here, but we'll just send some really gorgeous soft X-ray beams that we generate in these fibers. Then I just have a couple of slides on saying why is the VUV so interesting, because it turns out you might think it's got lower photon energy than the extreme UV. It should be easier to make light there, but it turns out it's been a long challenge. Our advisor's advisor was working on this when he was a grad student, and we've just sort of figured out how to make the light bright. Henry's looking at me like, okay. Doesn't matter. Okay, so VUV very important, of course, for photoelectron and photovoltage spectroscopies, for combustion studies, and of course June told us about these beautiful nuclear reference clocks, where normally nuclear transitions are very high energies, but there's a beautiful transition in thorium that occurs around 8.3 eV in the VUV region, and so that is the photon energy that we're targeting. As I said before, these beautiful anti-resonant fibers are great because they conduct light very efficiently, so we can do low-order cascaded harmonic generation. But if we use that process, it works great, but there's many steps still to reach the 7th harmonic, which is the wavelength of the nuclear clock. And so instead, what Jeremy, Drew, Emma, and Ivan have showed is that instead, if we just use a single step four-wave mixing process, so omega, 4 omega plus omega minus omega going to 7 omega, that process is insanely efficient for this region, 1 to 2% efficiency compared to 10 to the minus 4 or 10 to the minus 5 efficiency into higher order harmonic generation. So we suddenly have the ability to make enormous amounts of light in the VUV region at the transition that's relevant for this clock. It's got a beautiful narrow line width, 10 to the 5 times better scaling than if we use the highly cascaded process, and as I said, these enormous efficiencies. And the other thing that's happening is that there's a convergence of laser technologies where with the fiber-based oscillators and fiber amplifiers that we have the potential now to make a VUV light source for these clocks that could be rack mountable and transportable. And of course, they're of a great interest because they would be less susceptible to environmental perturbations than the regular atomic clock. Okay, so with that, I'll just summarize by saying, I hope I've given you some flavor of how high harmonic beams are just extremely interesting, both from their own light science in themselves, but also in applications. As I said, we don't know where the limit of this technology is, but we've already done useful applications. And I want to end by just thanking the current group members who are really bringing this technology from a sort of a scientific, beautiful scientific, light science into useful characterization and metrology tools. And I also want to thank my colleagues at CU Boulder, who we collaborate with at NIST, elsewhere, our industry collaborators, as well as the recent graduates who made this work possible. Thank you very much for your attention.
Thank you very much. I'm going to turn on the lights, and we have time for a few questions if people have questions. I saw your hand first. Please.
Different. It's different physics in that it's an extreme version of nonlinear optics, where the quantum phase matters. So there's an extra phase. So in regular nonlinear optics, you would push electrons beyond their harmonic part of the potential. But in extreme nonlinear optics, while the part of the wave function that ionizes is free, the laser is writing a quantum phase onto it. So you get extra ways to manipulate, and you get these nonlinear processes that are up to thousands of orders, which you can't do in a regular nonlinear process. it is the you can try to make an analogy with an anharmonic oscillator, but it really is the fact that you're making, in the strong laser field, you're literally plucking part of the wave function, forcing it to make a dipole transition from the ground state to the continuum, and then when it's in the vicinity of the core, it can make a dipole transition back. I like the quantum movie, that shows the radiating electron wave function, because that shows the very rapidly time-dependent dipole moment that's much higher frequency than the driving laser frequency. It's just the power. You literally needed the X-ray lasers that were demonstrated when Henry and I were grad students needed kilojoules, right? A laser the size of Nova, which is with the laser pre-nip, so it's a stadium size, Oh, you still would need, okay. There isn't enough power. Yeah, so we make a microwatts to milliwatts, which is fine for metrology. That's all you need to shine on the microscope. Yeah, that's more than enough. But exactly, yeah. And it's only one wavelength. So really, you want, for many applications and materials, you like having all the colors you can get, because you can image above and below an absorption edge, or you can track the magnetic state because the core levels of different elements are in different positions. So it is much nicer not to have just one color. Oh yeah, yeah, yeah. The guy doing it is sitting right behind you, and Andreas is and here, yeah. So there, yeah. It's hard. Okay, Ben can contradict me, but I think and Keegan and everybody. But I think it's the only way this field move forward is a little step forward by the experimentalists, and then the theorists, and then the experimentalists, and then 2 step backwards, and then forward. So, but I think now we are getting to a kind of a reasonable predictive place that you can actually design experiments, which is what Drew and Will and Michael are doing now. So it's much better than when we first were in this field. People had no idea. There were papers published, as is normal. It's just the scientific process, and many of them are wrong because nobody know. And the lasers were very big and clunky, and they only worked at 10 hertz, and you can't get good data. So like everything, the understanding has evolved, and the technology has evolved, so we can do it a lot better than we used to be able to do it.
So we're getting close to 5. I think I want to take one last question, and then we're going to maybe one last one.
Yes, that would be great. So the question is there any?
Oh yes, absolutely. And if we had the laser, we would be trying it. But no, we don't think. Who never say never, but we would be ecstatic if we could get to 15 keV. That would already be amazing. And there is no physics. there are ways you can play with, play with applied magnetic fields or counterpropagating lasers. So it's not out of the question. We might be able to get to 50 keV, but yeah, we're not writing that in any proposals right now. Mainly because there's so much to do in the meantime. There's, yeah.
But the question is, if you get to that, what you could
Oh, all kinds of things, because, medical x-rays are, you can't precisely control the dose very well, right? You could do backscatter, you could do all kinds of things. Yeah, it would be fantastic. Yeah. And
All right,
may even be possible.
Thank our speaker one more time.
Thanks, Tobin.